If you add two vectors together, you know that one arrow adds to the end of the other arrow. So if we have two vectors that define simple circular motion, you can write their equations relatively easily. We know that any equation that has this kind of shape, where the scale factor on the outside determines how long the vector is, and what you write on the inside here determines what angle it starts out at and how fast it's rotating. So what happens if we add those two together? Instead of having two simple circular motions, you get an interesting, more complex motion. Let's look at it a little faster. It traces a very interesting path, and this is what makes vectors so powerful. With vectors, you can add simple movements together to make a very complex movement. But if you want to make interesting, complex movements on purpose rather than by accident, there's two things that you have to learn how to control. You've got to be able to control the rotational speed of rotating vectors, or if you've got a vector that's stretching over time, control its linear speed. So let's get started. There are two key definitions that you always want to come back to, and I think you know them already. Linear speed would just be some distance that you traveled divided by how much time it took to travel. So if I went, for example, 10 feet in 3 seconds, I would be going 10 feet divided by 3 seconds, or, let's write it down here, so 10 feet over 3 seconds is 10/3 feet per second. Okay, let's think how that applies to vectors. Let's say this vector determines my movement. There's a lot of numbers here, so let's not guess at what numbers are relevant. Let's go back to the definition. I'm at a particular location at a certain time, and then later on, I'm at a different location. So let's look at two different times and think about what distance did I travel and how long did it take. So let's think about time equals 0 and time equals 1, for example. That would be a change in 1 second. Okay, where am I going to be? So at time 0, if I plug in 0 here, that scales this entire vector to length 0. So my actual location is just right here at 3, 3. So there I am at time 0. At time 1, I'm adding the 3, 3 vector here, plus 1, 2, 1 vector. So that means I'll go over 2 and up 1, and I've added that vector. So if I'm here at time 0, and I'm here at time 1, you could calculate, like, what's the distance formula between these 2 points. But actually, if you think about it, the distance that I walked was just this diagonal distance. I walked along this vector. So it seems like in the 1 second, if I started here and ended there, I just traveled that far. And we know a word for that. That's the magnitude of the vector. So if I think about how could I calculate that magnitude, it's the Pythagorean theorem. So that's going to be 2 squared plus 1 squared is root 5. So every single second, I'm walking along that diagonal vector whose length is root 5. And so my total speed must be root 5 feet per every second. And I'm assuming here that our units are in feet and seconds. They could be other units. Okay, so the big takeaway here is if you have a scaling vector and you want to know how fast the motion is, all you have to do is look at the magnitude of the vector, because that's saying the path that you're traveling along with every additional second. Warning, you must always think about what you're doing and if it makes sense. So I don't want you to take away, all I have to do is find the magnitude of one of the vectors, or like maybe the t vector, and then I'm done. Because what happens if I have two vectors that are being added, that are both being scaled by time? The speed I'm traveling at isn't the magnitude of this one. It's not the magnitude of this one either. It's also not the magnitudes if I find them separately and add them up. So you can't guess at what's going to happen. Go back to the definition. Let's think about it again. I'm at a particular place at time 0. I'm at a particular place at time 1. And let's think about it. So at time 0, I have a 0 length vector plus a 0 length vector. So in this case, I'm here at time 0. At time 1, I've gone up by 3. I've traversed the 3, 3 vector, and I've traversed the 2, 1 vector. So I'm right here. But I don't actually walk along this vector and this vector. Remember, the vector sum is what you get. It's a single vector that represents the path if you were going to start at the beginning and end at the end. So I'm actually walking along that diagonal line. So in this case, you could think about your ending position. 3 plus 2 is 5. 3 plus 1 is 4. So here, the length of that hypotenuse would be 5 squared is 25, 4 squared is 16, which is root 41 is that total distance. You could see that if I was going to add these together. Remember, this is the same thing as saying 3t, 3t. This is the same thing as saying 2t, t, because I just multiplied the t in. And now I can add them together, the x parts and the y parts separately. So 3t plus 2t is 5t's. 3t plus t is 4t. And if I'm going to take the t out now, you can see that that's the same thing as scaling the 5, 4 vector. So, and the 5, 4 vector is exactly this vector right here, which we found the magnitude for. So the idea still works. I'm still traveling the magnitude of my vector. It's just that if there's more than one vector that's stretching, you have to think about how they combine together, because that's the actual movement that I'm making. Okay, come back in the next video and we'll talk about rotational speed.